Please note that this is a sponsored event and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors of pricings of products and services. And now, without further delay, welcome to Trenchless and HDPE, Stretching the Limits with Proven Success. This is the first webinar in the 2024 series of 4 provided by the Alliance for PE Pipe, WL Plastics, and Core & Main. Each of these webinars in the 2024 series will be 75 minutes. We are all so excited to get an extra 15 minutes with this fantastic team. And now it is my pleasure to welcome back for the 4th year of providing valuable HDPE sponsored webinars with ASCE, Peter Dyke, Executive Director of the Alliance for PE Pipe. Welcome back, Peter.
Thanks, Robin. Thanks for having us back for another year. We're delighted to be here with you and your members of your great organization. We've really appreciated our alignment with you all, and that of Core & Main and WL to help us afford to speak to your audience. So thank you for that, and welcome back to our audience for the first of 4 series of polyethylene-oriented webinars. Alan Ambler's done a fantastic job of putting a deck together today for you guys, and we will get started on that right now. So these are the companies that help fund our operation. We take that gas from the wellhead, that ethane, we crack it, we turn it into polyethylene pellets, and we melt those pellets and turn it into polyethylene pipe. And that is what we're talking about today, but how do we install it? And as many of you know, we have a social media program we post every day, and LinkedIn is our most engaging of the formats. So we like to use LinkedIn a lot. We're in Portland today doing a road show. We've got a training together with Core & Main tomorrow. Then we're out on the coast doing another road show on the coast of Oregon. And then a week from today on the Alliance's webpage, we have the inclement, also known as the cold weather webinar. That'll also be 75 minutes. And I do want to say, Robin, thank you for giving us 15 more minutes of time. You know, on our page, we keep 98% of our people through these 75-minute webinars. Sometimes we find that 60 minutes is just a little bit too short. So thank you, ASCE, for that. And then Alan is working on another webinar on March 5th on hydraulics. So Alan, if you could tell us a little bit about that. Alan Ambler, please come on the screen. All right, well, he'll tell us about it in a few minutes. All right, Alan, could you advance? Hey, there you are.
Hey, Pete, sorry. Yes, flow and hydraulics. We're looking at complicated potable water distribution system networks or force mains to be able to look at the hydraulic flow within that. And we're teaming up with some great guest speakers to talk to us about hydraulic modeling. And the positive effects of high-density polyethylene pipe at that time as well.
Hey, so, Alan, sorry I misspelled flow there. My bad. Yep. All right, next page. All right. So also from the Alliance is many of you send us a question in Q&A, as Robin described. We will help you with your project. If you have a specific question, we'll just respond to you and we'll get out of your way. But if you want to work in greater detail, we can do that as well. And Alan has just completed a full review of our specifications, and those will be up on our website later this week. We're excited about the project-specific or installation method-specific specifications that are now available to you. Alan Ambler has also put together some great standard details for your AutoCAD library. Those are available to you free of charge. You could also send us a Q&A and say, hey, please send me the engineers package. And Alan and his team of engineers will send that engineers package, which basically establishes your polyethylene library. Next page, please, Alan. I also wanted to mention, since some of you pay attention to what Engineers Without Borders are doing, we have teamed up with them and we're doing a poly project in the mountains of Peru. Very excited about that. And WL has contributed a bunch of pipe for that. And we're going to help install polyethylene pipe at elevation in the mountains outside of Lima. And that project will go on in October of this year. And this next screen is, we got our hands out. We are asking for money. So you can just go to the Washington, D.C. chapter and contribute 25 bucks. We would love it if you would do that. but no big deal if you don't. Anyway, we're engaged with the Engineers Without Borders. So here on the screen, you can see if you do want to connect with my engineering team or WL or Core and Main, you know, we're vertically integrated here. We're the educators. Core and Main can help your contractors deliver those projects. You can email anybody on this page and get answers to your questions. So maybe you want to take a screenshot of that. And we also want to acknowledge the many people that helped us produce this deck. This is a new deck. We've never presented it before. Certainly some of the slides might be familiar if you hung around with us in previous times, but we thank the many companies that are active in the polyethylene space. And today we have Richard Colassa and Rusty Reeves. Guys, could you come on? And Rusty, let's start with you. Tell us who you are and what you do. And thank you to the Core and Main team for sponsoring this program today.
You bet. You bet. Thanks, Peter. And, we're really excited about this. I think we're going on our third year that we've been doing this. And again, it's very key, I think, to get information out about HDPE piping systems. I've actually been involved in HDPE for over 30 years and joined Core and Main. And we have over 350 branches nationwide. We have over 700 pieces of equipment. And really want to support anyone out there who is wanting to continue these projects. Again, no dig, I think, is a big growing area as well. So again, thanks to the Alliance and also to ASCE and Robin for letting us get involved.
Yeah, well, we appreciate your support, Rusty, for sure. Richard Colassa, tell us a little bit about you.
Hey, thanks, Peter, and thanks to ASCE for holding these events again. We feel that they're a great medium to kind of send out messages and making sure that things are being done properly with our products, so they people get the benefits from what they can do. We're a polyethylene pipe manufacturer, fairly large in the U.S. and North American market. We also ship overseas and even down to the Mexico area as well. But I've been doing this for almost 40 years now. I hate to say it, but it's been a long time. But it's something that's really beneficial to me and been very rewarding, especially when engineers like yourselves come online with today and try to educate yourselves, because we think it's a very, very important message, and we appreciate the time that you give us.
Yeah, well, we appreciate you guys too. Thanks for helping move the needle. I also want to apologize to our audience for messing up the link for those people that signed up on the Alliance's website. That was my bad. Brian Dorwart, please come on and introduce yourself, and Alan Ambler, please as well, guys. You're the big show today. So Brian, let's hear from you.
I'm Brian Dorwart from Brierley Associates, and I would like to thank ASCE. One of their main objectives is getting information that's important to successfully completing a project to people that use this information daily. I'm very pleased to be part of that. It's one of my personal goals in life, to make sure we pass on the information to others in our field. I've been in the field of trenchless design as an engineer and designer for about 40 years now, starting with large tunnels and ending up with anything from sewer rehab to HDDs. I've done some quite large HDDs with poly pipe and some very small ones, a very successful product. So with that, thank you very much for having me on here. I appreciate the opportunity.
Well, for those of you who don't know, Brian is a legend in the underground construction and the poly world. And, you've forgotten more than I'll ever know, Brian. So thank you very much. And Alan Ambler, you've put a wonderful deck together today. And thank you for using your resources to put this deck in this space and make it available to all these folks.
Happy to be here, Pete. Lots of love for education, and that's one of our primary goals here at the Alliance for PE Pipe, is to help make sure that anyone that wants to learn can use those appropriate tools. So we're happy to help.
All right. We also have, Alan, what we call the bench. So we've got a bunch of people who are already starting to answer questions that are being asked of us. So we've got Steve Breedemeyer, we've got Dusty Langston. Dan's not making it today, but I think we have one other person there, Alan, or not?
Nope, that's who we got on the
Okay.
bench, Pete.
All
So,
right.
and Pete talks about this. We have a parallel program going. So not only do you get to listen passively and learn from the presentation that we have, but when you got that burning question that's already right there at the tip of your fingers and you want to type it, feel free to do so anytime. We've already been asked a question about open cut and soil surrounding the pipe and what would be considered safe for that. So definitely thank you all for those questions and keep them coming. That's what we're here for. We got a nice bench supporting it in the back. So,
All right. Let's get this kicked off. And Alan, you're starting off with this Tucson project. This is a fantastic BNF job. Why don't you take it away? And I will fade to the background and work the bench.
okay, Pete. So we wanted to start off with some case studies, real quick, simple, to show you some of the pushing the boundaries that high density polyethylene industry is doing. Also, several of you throughout the webinar world for us have asked us questions already in advance of this. So we're going to take a couple of slides and explain some of those answers to those questions that you've already sent to us. This job in particular, Pete and Dan got to visit last year, and they are repurposing a pre-stressed concrete cylinder pipe that was otherwise abandoned. So they were able to line that pipe with 30-inch and 32-inch high-density polyethylene. The agency itself had thought that this space for utility was just never going to be used again until they recognized some of the alliance's messaging and also examples, case studies, some people that have gone through and repurposed pre-stressed concrete cylinder pipe before. When we talk about pipe bursting in a bit, this is also one of those pipes that cannot be burst. And you can imagine why, seeing it on the left that an expander head or cutting blades won't simply go through this pre-stressed concrete cylinder pipe. There's lots of pre-stressed concrete cylinder pipe throughout the country. Some of it, much of it is coming to the end of its service life. And please keep that in your head when you're looking at alternative analysis to be able to use high-density polyethylene to repurpose this. So we've got some information for you here. This video is showing us just to the extent as to we are using that natural property of a high-density polyethylene and that bending radius, allowable bending radius, to come right through, avoiding bends or otherwise to be able to pull that into place. Pretty impressive what we're doing out there in the rehab space and also new installation space. So here's a Colesman Tunnel Rehabilitation Project. This is another slip lining application used for a tunnel. So new tunnel costs through this location was looking at 30 million, but that slip lining is only 8 million. So we saved a fairly significant amount of money for this agency by repurposing this tunnel that was failed in that scenario. So here, as that pipe gets bigger, so do the logistics of handling that pipe as we come through it. So you'll see all of the equipment now starting to scale up and get larger as we're dealing with the appropriate butt fusion equipment to be able to make sure that that joint that we're fusing together is as strong, if not stronger, than the pipe itself. And now we're fusing a pull head on this to be able to facilitate slip lining through this tunnel as we go through. And quite a bit of pipe lengths and definitely there's some logistics in being able to fuse all that pipe run up in advance. And one of the key things that contractors recognize with experienced installation contractors for high density polyethylene is the longer that run we can fuse up in advance, then we'll take advantage of the fast installation methods of a trenchless technology project to be able to maximize that productivity. So here we're looking, getting some of the details into putting it into the East Portal Tunnel as we're seeing here. Just a reminder, everybody out there, if you've got a question, please try to load it up into the questions and answers session as opposed to chat. We'll be able to see it a little cleaner that way and be able to answer that question for everyone that's on the webinar. So here we are. After the pull is done through this tunnel, that we've got a swivel, we've got multiple different pull heads to be able to diffuse that pull force as we go through. And we are repurposing this as well. So here's Seattle Public Utilities and the Tolt pipeline. This one originally was installed open cut, and now we're installing this via slip lining into an existing pipeline itself. Raw water lines had been abandoned for several years, failing concrete pipe, and then also some seismic events that shifted that soils around the existing pipeline as we pulled that through. So you'll see some of the contractors here had fashioned, field fabricator to fashioned the pole head to start to slip line that process through it. This really proves the ruggedness and durability of high density polyethylene and the sheer things that you can do to polyethylene in the field, and it still is a very good product as we go through. Obviously, this pull head would be cut out and terminal final connections would be made on the clean high density polyethylene through that, but this really are just illustrations, therefore, of what we can expect to work with for high density polyethylene. Brian, you want to come on and talk to us some about this large project? We spoke before. I believe you worked on the south end of it. This was quite a large project in Fort Lauderdale. That was an emergency project as Force Main was leaking water into the intercoastal, if I remember correctly.
Yes, sir, it was. It was a series of fairly new pipes that were put in that corroded. And once it corroded within about 5-6 years, obviously the main line there was out of business. So the idea, because it was an emergency action, they split it into 2 contracts. Both contractors had to put in 54-inch diameter HDPE pipes, right pretty much parallel, and then tied into the existing valve system and the existing sewer system, all in downtown Fort Lauderdale, while still keeping the streets active. Is quite an event. It came in pretty much on schedule and on or slightly under budget. Commended to people like Murphy's Brothers and Dave Mancini and Sons for the 2 contractors that had to work out the logistics under very difficult conditions to make this happen.
If I remember correctly, they had vac trucks going 24 hours a day. So just that bypass alone must have been a pretty large expense through this whole process as well. So.
Yes, sir. The bypass pass is, of course, can almost double the cost of a project. So certainly consider it whenever you're doing a project.
I always ask, one of the first questions I always ask is whether or not that line is redundant for us. So that's definitely a big one here. So multiple trenchless methods were used, if I remember correctly, with compressive fit, slip lining, horizontal directional drill, and a few others. Is that right?
That's correct. There was a number of different types of devices. Depends on which one was most practical at the time, and also what pipe was available. You imagine an emergency situation with 54-inch pipe. It's not a pipe that's sitting on the ground. And manufacturers came through and delivered this to meet a very difficult schedule. It was very pleasing to work on that project.
Oh, great. Well, that's certainly better than most of them being a pain in the butt. So sometimes we get those too, right, Brian? So here's another drill that you were a part of, if I remember correctly. Let me mute that while we talk through it. This one's 4,500 feet of 54-inch DR17 for Miami Beach, correct?
That's correct. We had to run this one down about 45 to 50 feet. DR17 is not really made to go that deep without having something in it. This is the first time we went with this size pipe. You can see the video there showing 2 of them. We actually had to fuse the 2 of them together. One of the biggest problems there, we're right on downtown South Beach, and right next to South Beach is 1 block over. So we had to make all our work happen without interrupting the businesses in this area. We broke it into 2 bores, 3,000 and 1,200 foot, and both of them went very successfully and came in under the pull force calculations, and the pipe is now in action and working very successfully.
Great. That's a common theme with these past 2 projects there, Brian. That's very good to say there for you. So Great. So we had a couple of questions already, and I love to see them coming in. So terminal connections, how after we pull this trenchless into place, what are we looking at? There's two primary things that we need to take account for and really pay attention to, and that's the Poisson effect. Richard, do you want to come on and tell us a little bit about Poisson's effect here? And as an operating condition, once we charge that pipe, what's going on?
Yeah, exactly. And as Brian mentioned earlier, it's one of the things that are kind of forgotten about installations, especially on starting up the lines. When we apply any kind of pressure to polyethylene pipe, because of its ductility, we have forces in every direction and in kind of in a hoop stress direction. And what that does is it actually expands that pipe a little bit because of its ductility. But don't let that scare you, because the ductility is actually controlled by the polymer itself. We only allow in pressure testing a maximum of 5% of expansion. But if you take a 54-inch, 4,500 foot length in Miami and you expand it a couple of percent, that's a lot of water volume that you have to make up. Plus, it will actually shrink the length of that pipe. So you have to calculate those forces and understand those forces that are being applied to those connections, so you don't pull those joints out. If you have a compression tight fit, that might be a concern. But if you do fuse the pipe onto something else, then that is now becomes self-restrained. So you don't have to worry about those as much, or at all. So just be cognizant of Poisson's effects when we pressurize. And I just had several conversations in January about pressure testing. You do have to use makeup water, and I'm assuming that all the air has been taken out of that system, so you don't have compression of the air. But if you assume all that air is gone and you do conduct those pressure tests, you will see that expansion, and you will have to make up that water. It's not a leak. Because typically in a leak system, you can't hold that pressure. So what you'll see on a pressure test, for example, is that pressure slowly decline back down. And then once you make up that water, it'll get less and less once that expansion has completed itself from those Poisson's effects.
Okay. And then we look at thermal effects and a lot of installed pipelines. If we're conveying a fluid that doesn't change in its temperature, the installed thermal effects really is a temporary condition. So that pipe is sitting above ground, warming up with the sun until we're ready to pull it into place. And then after we pull it into place, that pipe will relax prior to making those final connection. So one of the unique things of high density polyethylene is this modulus of elasticity and how different it is from carbon steel.
Hey, Alan, we're losing your connection. You may want to turn off your camera to save on bandwidth.
From that expansion, never less than that what we would see of carbon steel. Yes, Richard.
Yeah, so and this, just a note, this is in addition to Poisson's laws when you start up those lines as well. So when you pull that pipe in, make sure that you take these forces into consideration, especially on startup, if they have not stabilized yet, or if you have a changing condition over time.
Brian.
Yeah, just a quick comment on the pressure test is that turns into a bit of a headache on a number of testing I've seen. Simple way to fix that problem is once your pipe is filled with water, overpressurize it about 10%, give it a little bit of time, and then depressurize it down to your test pressure. That'll get the air absorbed into the system and let your test be a lot better chance of being successful.
Okay, and that procedure is available in a Alliance for PE pipe specification specific to pressure testing as well. So there, those unique things that we see with HDPE's behavior are addressed in the specifications that are available to you as well. Thrust restraint in polyethylene world, every bead every fused joint is considered restrained. It's considered to be a restrained joint. So when we look at thrust restraint, we want to make sure that when we're connecting to alternate pipe materials, we are not going to pull that bell and spigot pipe out of the bell and spigot, because there's no restraint force around that bell and spigot itself. We're not detrimenting the polyethylene. So if you were polyethylene from point A to point B, you'd be a fully self-restrained monolithic system. It's when we connect to other material types that we want to make sure that we are using a restrained joint and not pulling that other pipe out of its bell and spigot as well. So what does this look like? Go ahead, talk to us, Pete. You're on mute.
Sorry about that. I got a great question, Alan, I'd like to share with everybody about what is the proper procedure for testing a pipe string before you pull it in the ground? Is it 1.5 times working pressure for 10 hours, or what are the rules?
Okay, so that's a great question. And what we'll see, Pete, is there's a difference between operating pressure of the system and then design pressure of the pipe. So as engineers, we're fairly conservative folks. The potable water systems have adopted DR11 primarily for their pipes. DR11 happens to be a 200 PSI working pressure system. You could charge that to 1.5 times that design pressure, but now that's quite a bit of pressure that we're achieving in the field. What's typically used is the operating pressure of the system that we're installing, and then we are amplifying that 1.5 times for a duration in order to be able to overcharge the pipe, as Brian had mentioned, and then we lower that pressure to continue to operate or observe that pressure test to make sure that we're not losing any water. Any amended water that may be added to a non-leaking high-density polyethylene pipe could be because of that thermal effect and that Poisson's effect that we talked about. Yes, Brian?
The one quick comment I have on pressure testing is a lot of times when we do pressure testing on the ground surface, we'll try with a pneumatic test as opposed to a water test. The reason for that is safety. No matter how careful you are and how good you are, those caps at the end or any other place have an awful lot of sectional area. They will come off ballistically if something fails. So it's a safety concern as much as anything else. Once you're in the ground, it's not a problem. You're contained. So just be aware of the safety aspect on anytime you do a pressure test on any pipe.
Absolutely. Great comment there, Brian. I really appreciate that. And the last time I've done pressure tests in this manner, I have the same nerves about that end cap coming off. So, but once we restrain it properly to the HDPE pipe using the restraints that you're seeing here, this MJ adapter is that belts and suspenders, very heavy duty, lots of a good material within this adapter. It can also be done in wet conditions, unlike fusion. So that way, if you've got a leaky valve that simply won't seat and you have some water in a potable water system as we're connecting, you'd fuse this MJ adapter on in advance and then pull it right there. Same connection to valves. The industry itself does not have HDPE gate valves. Now, HDPE ball valves have started to be used in larger dimensions and larger sizes in irrigation. They just haven't quite made its way to the municipal water and wastewater market. So we do have to have the MJ adapter or another type of fitting to be able to attach to these valves to be able to control that flow as we go through. And terminal connections, there's lots of agencies out there, such as Core and Main, that can come on. Rusty, if you wanted to, and talk to us some about some of the fittings that you're going through in these manners. There's a lot of different things that you can put together and fabricate for somebody to make those terminal connections. Isn't that right, Rusty?
Yeah, I think that's one of the great things about the increased use of polyethylene in the waterworks systems and everything. It's very established. It's been around since the 60s, 50s, and 60s, and kind of started in the industrial side of it. But with the proliferation of the no-dig applications and everything, we have a lot more fittings involved. Again, any type of connection you want to do with polyethylene, if you can fuse it, it's going to be the best way. You're not adding a third or second material in there. You're not putting a gasket, metallic, anything else. If you can keep it polyethylene, which you do with fusion, butt fusion, then you want to do that. So we have in-ditch butt fusion equipment that we can do up through 63-inch to do tie-ins. We've done over 500 fusions with this equipment, and it's just great for doing those tie-ins and getting into those small places that you need to do. Of course, you can't, sometimes you can't do that. It comes out, you've got electrofusion as a backup, and that's really your second thing that you would want to use. And then from there, you go into the mechanical type, either flange by flange, MJs like you've shown before. You've got all types of saddles that are also available. Ideally, you do want that fusion if you can, like we talked about. Even flange by flange is really good because the best gasket material you can use is like a Teflon material. Well, that Teflon has the same durometer as HDPE. So if you're going new to new on flanges, you don't even need to use a gasket in there. You bolt that together and it's going to give you a zero leak rate system, which again is one of the probably biggest positives of using HDPE piping systems. But there are a lot more fittings and everything out there available now than there was 25, 30 years ago. We can do just about anything. So the other thing about that is with the fabrication and everything, we've got fabrication all over the country, large CNCs going up to 60-inch and everything else. We can do any type of transition you need as well and maintain the fusion as we talked about. So if you're going, IPS to dips or dips into another material, like you mentioned, Alan, you're going to a ductile iron or PVC or fiberglass, whatever it happens to be. We can machine that transition to where you're going to have a good clean fit.
Great, great. We're about 45 minutes out here and we're cruising right along. So thank you very much, Rusty. Brian, we're about ready to start onto your HDD section. If you'd like to comment here at these butt fusion machines in the excavation, you're more than welcome to as well.
I appreciate it. I just have one quick comment because it regarded safety, which is near and dear to all of our hearts. There's a question: is the pneumatic test using air pressure has much greater volume and can be just as nasty as a water test, hydrostatic test? Very true. That's why the pneumatic tests are usually recommended to be only at about 3 PSI. You still want to have a good connection at the end and use the soapy water to look for leaks, because that's really what you're looking for. Just put some soapy water. If it bubbles, you got a problem, and you only need about 3 PSI. You do not need to go to 1.5 or 1.2 times. That would be way too much pressure for what you're trying to accomplish. Thank you.
And Mary, thank you so much for that follow-up. So here we'll roll right into HDD. Brian, come back on and take her away, bud.
Sounds good. I appreciate that. I'm going to talk a little bit about HDD, horizontal directional drilling, and the use of polyethylene pipe. So be pretty much focused on that. With the this type of pipe and this type of engineering, you'll find it different from other types of pipe. You need to be both a pipeline engineer and a pipe engineer. There's a distinctive difference, and I'll be going through that in the discussion here. And that's irrespective of whether you're talking small, large, or double stacked in type of, like the force main in the middle there, or the real long one, which is South Beach, Miami, trying to handle the pipe into the ground. You need to be careful about actually designing the pipe. There's a pipeline engineer, which designs the geometry of the bore, and there's a pipe engineer. You have to look at your materials, understand what you're working with to make sure that what you're designing will work under your situation. More failures out there occur because of lack of proper consideration for the materials that you're working with. Nothing wrong with the materials, but be conscious. And they're very well published materials. So between that and the only other quick comment at the beginning here is production rate. It controls your pricing on any project. So if you have rock, it's going to go slower. It's going to cost you more. If you're in soil, you can get less cost. It's not the contractor changing and playing games with you. It's what the ground will let you do. Next slide, please. So with that, just give a basic of what horizontal directional drilling is. It starts out with a pilot hole, which you have to steer through the ground. A whole bunch of different steering techniques out there. You can either use a wire line, a walkover. It's very dependent on the type of conditions you have. And this is the type of thing that once you have a project lined out, discuss this with steering experts. Find out what's going to work best for your system to be able to steer it from one side to the other. Next slide, please. The next step is you got to make the hole bigger, unless you're just doing what's called a drill and pull, where you drill the pilot through, grab your product pipe and pull it back. But a lot of times on the bigger pipes, you got to make the hole large enough to pull your product pipe through. That's what the pre-reaming is for. Usually you bring your pipe up, just rule of thumb is 1.5 times bigger than your pipe OD. That can be changed around some techniques, and people have gone as tight as no difference. So this is a general discussion of how the HDDs are done, not the only way they can be done. So be aware there's other ways that things can be done. Once you have the hole prepared, you clean it up by pulling a swab through the hole. Make sure you got mechanically removed your cuttings in your hole, whatever's left over. Grab onto your pipe and pull it through. And this is where you need to pay attention to your pipe materials. I don't care what kind of pull you have. If you have a good hole, you can calculate fairly reasonably your pull, and that'll tell you how far you can go. That's part of the planning process. Next, please. With regard to design, all right, the design is, at least in my opinion, design is basically planning your job, trying to anticipate issues that may occur and fix them. That's part of that is selecting your materials, selecting your material geometries, and your material cross-section areas, properties, etc. And then remembering that design, just like what they say in the Army, all your plans, your design, they're only as good as the first shot in the ground. Be flexible, work with it. It's a planning tool. If you try to use it as the contractor will do this no matter what, you're probably going to be disappointed. Next slide, please. As I mentioned earlier, these are the different types of steerings. They require different work areas and different accesses to the site. One of the main things is, it sounds like trenchless. Well, you only need to have one access point at one end and a receiving at the other end, but somehow you got to steer things. And when you talk about things like a walkover, all you got to do is be able to walk across your site. Well, if you're doing that in a 4-lane highway, there's techniques that are available to assist you with that, even with a walkover. Or you may have to go with a wire line, which is a little bit more precise with depth, or you might have to go with a gyro. Each one of these has pros and cons. This is why once you come up with a project, it's really beneficial to talk to an expert in steering to get the type of steering you need to accomplish what you're trying to do. If you want to have a pipe within 1 foot of a particular location in the ground somewheres, you're going to be adding a lot of cost. Not that it can't be done, but that's up to your steering people. Find out what it's going to cost and what you need. The other one is know where your utilities are. This is right up front. There's people that do this. The SUE engineers do this frequently and survey it in. The reason I put the top picture in, we found out that's actually a main water supply servicing a couple of million people in a major metropolitan area. And we found out once we dug that pipe out that the hole started in that pipe, the actual hole, it matched exactly a reamer dimension as it snuck by. Pilot made it by, reamer did not make it by. So pay attention to what you're doing, pay attention to where the utilities are. And basically, rule of thumb, give yourself as much clearance as you can get. It's going to help you immensely. Workspace. Directional drilling does require heavy equipment. I know all we're doing is we're putting one little hole in the ground, and all this equipment is so we can put one little hole in the ground, but the equipment takes space. On the left is a little bitty space that's doing a house connection with a little bitty micro drill. And that would be typically I'd use polyethylene pipe on that, put it in, take it out, connect it to the main for telecom or whatever else you need, and even a sewer connection, you're done. One on the right, that's a much larger connection for a 1,000,000-pound rig, 1,000,000+ pound rig. That takes about 250 feet by 200 feet or 175. There's lots of different things in it. Give yourself enough room, and a lot of times I go 400 by 400 on a real large system, only to give trucks that are servicing it every day a place to turn around. Next slide, please. So, and the other thing is what your needs are going to be in an entry area. Say you have something 400 feet long and only 50 feet wide. You got to understand your drill rig's probably going to take 85 feet from the front end of the drill where it goes in the ground to the back. You need to have available space that allow the drill rig to fit in there with all this other appurtenances. The other thing is on the entry pit there, a lot of times that's a place where you can lose drill fluid, and we'll talk about that in a minute. But a lot of times what I'll try to do is make that drill pit where the drill goes in the ground about 50 feet behind my construction barrier or environmental fence. If anything happens, it's usually a lot of times in the first 20 feet vertical of drilling, getting down to a 20-foot depth. If you have that buffer in there, you get to control it in an area of your choosing. The exit, look for enough space to put all your pipes together. Ideally, full length. You can't always get full length. Like in South Beach, we were limited to length. We had to fuse them together. Look at the quality of your hole. Make sure you can make a hole that will stay open long enough to actually fuse all these pipe sections together. If you're pulling a bundle, treat your bundle just as a single pipe with the same OD. You can get fancier than that, but that usually will give you a good enough feeling as to what kind of curves, lifting, stresses, etc. you can put into it. Next, please. Geometry, exit and entry angles. Those are typical rule of thumb is 6 and 18 degrees, somewhere in that range is what they can do. But a lot of times I try to limit to 8 to 12 degrees because it's a convenient dimension to go in at. You're coming in steep enough to get down soon enough to your design depth, and you're coming up at a reasonable degree where you can actually bend the pipe to fit it in the hole without having to lift it up. So that exit is very important because you got to still get the pipe in the hole, which means you got to bend it from horizontal down into the ground. If you bend it too far, coming up too steep, you're going to have to lift the pipe up in the air. Anytime you do that, it becomes a safety concern. The nice thing with HDPE is that it bends a lot. So you can leave it generally on the ground, just round your exit pit a little bit, and the pipe will pull in just fine, saving you a lot of safety heartburn. So also look on your rig capability. I've had certain times where you can't move the rig back. Think about in terms of there's no reason you can't dig the front of the rig down a little deeper and accomplish wherever you're going to intersect. So your design path. So entry and exit angles can control how your rig is set up, but they should be kept at a reasonable degree as possible. Next, please.
So, Brian, one of the things that I'd like to just reinforce with everybody out there, this entrance and exit angle limitations are easily one of the biggest errors that engineers that are not familiar with HDD design make upon initial thoughts for them to, just how fast we can clear that obstacle, right? We're not going to do a 30-inch horizontal directional drill 20 feet deep in about 200 feet. Isn't that correct, Brian?
Absolutely.
All right.
That's a good point, Alan. You're not going to do a 200-foot creek crossing with 30-inch pipe in a 200-foot length. It's just some things are, find another technique. It's not your right solution.
Okay, great.
So then it comes, and this is where you got to understand your material properties, because you see on your geometry, you have to actually design the pipe. The way it's on the picture on the right there, where it's bending down in the hole, you got to make sure you can bend that pipe. And there's plenty of information out there on pipe bending, how much it'll go before you start buckling it. If you were to pick that pipe up at a hard point and bend it too far, you're just going to kink your pipe. Yes, you can straighten it back out again for HDPE, not for steel or any other pipe. You'll break it, but pay attention to your material properties. That's what pipe design is. Understand the properties, use those properties to verify that what you're asking the contractor can do can be done. You can see the difference between the pipe on the right and the lifting down in the bottom there where we're putting in a steel pipe. You have all sorts of construction concerns. You got to lift it up very high. Not only that, but that pipe is moving left to right. And as it's doing that, it's trying to pull those little supports over, tipping them over. They have tipped over. So you do have a safety concern there. So the nice thing about HDPE pipe, you can keep it down low to the ground, still properly support it. But again, know your properties, know what you're going to have to put on it as far as loads for radiuses and proper support for the pipe. And also recognize HDPE, you don't have to be so careful with your lifting that you're going to damage coating, because the pipe sort of takes care of itself that way. Next, please. That's where you get into bend radius. We did talk about that a little bit earlier. Bend radius is pretty well published as far as HDPE, how much it can bend. The issue I run into more times than not with bend radius is people look at in terms of, well, when my pipe's in the ground, that's my bend radius, and that's what I got to use and make sure I can put it in the ground. Well, the problem with HDPE in this case is you need to have a drill rig if you're using HDD to put it in, and your radiuses are going to be controlled by your drill steel, not by the pipe. So you got to make sure you can actually construct it. Otherwise, you're designing something, and if you're designing to the HDPE minimum radius, you're designing something that is not going to be likely built using the HDD process. So again, know your pipe, know your materials, know what is going to control your design as far as your geometry of your layout. It can be the drill pipe or it can be the HDPE pipe, but 99% of the time, you'll find it's your drill steel that's going to control it. And that doesn't mean you go to your drill steel manual and find out what the sharpest radius is. If you do that, you're going to exceed your bend radius at some time, because the contractor is not perfect. Double that at least. It's a little planning tool here that can help you at least, and this is available on the PPI website. It can help you both with your pipe selection. So once you've figured out how much energy it's going to take or how much force it's going to take to pull your pipe in, make sure you have enough thickness, which is registered by DR. Make sure you have enough thickness for the size pipe you have to actually give you enough strength of that pipe to pull it in. The other side, the nice thing about this, you got a little calculator in this as well on the left there, that say you put in L3 at 0. Well, if you have L3 at 0, you have only your pipe entry and your exit angles controlling. And if you bring them up to the ground surface, not a good idea. That your bore has to be a minimum of that length. It can't get shorter. Good rule of thumb, though, is on your entry, before you make your vertical curve, have at least 2 drill rods in the ground, preferably 3, and that's your bottom tangent, L3. Try to have at least 2 or 3 rods in that area to allow your contractor to make corrections should he have difficulty in the ground. Again, the tighter you make your tolerances, the more expensive it's going to be. Give your contractor a chance. Next, please.
Lots of great questions coming through. These planning tools were asked by Anthony Marucci not too long ago. So definitely keep asking those questions, and we'll be able to share as much as we possibly can. Thank you all so very much.
If I can't get them on directly, I will certainly follow up and get you an email for sure on these things. Pipeline design, this is what I've been harping on a little bit there. You can see you have to design for the materials. This is our connection at the ends of two HDPE drills down in South Beach. This is where the 1200 and the 3000 came together. Notice the type of connection. It's a very rigid connection with fused on, and then bolted together links to create a secured joint. You want to make sure that stays secure, because right here I have a pipe that I actually have to tap in yet and go sideways to connect to the existing system. So know your pipe material, know the strength, because Poisson effect comes into play here. Temperature comes into effect. Your pullback strength. In this case, we had an issue with, we couldn't get all DR17 pipe. So knowing my material strength, we actually worked with a DR17, a DR13.5, and a DR21. Well, if you know where your loads are going due to your proper pullback, you put your strongest pipe where your highest loads are going to be, and you can get away with a weaker pipe at the other end. But it requires knowing your pipe materials, knowing how to design for success of that pipe and what you can get away with. That's the thinking on the fly. You won't be planning it that way, but you got to do that because sometimes life happens. Knowing your materials allows you options.
It definitely does there, Brian. So one of the unique things about HDPE is you're allowed to fuse one DR change in either direction, but not more than that. So your DR17 can be fused to a DR13.5, or the opposite direction, the DR17 to a DR21. Richard's going to expound a little bit more on that topic.
Yeah, just make sure everyone understands that the high density properties that we design for piping in the PE 4710 are the cell classes that we design for these applications. So we understand that it's not just a random number that we're choosing. We looked at your operations and how they operate and how they need to be installed. So those are typically available in ASTM D3350. So it's great information to understand, but like Brian says, understand the material is so important, because then you understand the limitations of what it can and cannot do.
Yeah, thank you very much. That's very important, is understanding your materials. And as a quick example, your pullback force, if you go by the tables for safe pull load, you actually have a factor of safety of somewhere around 4 in there. So what happens if you get to that level that you've calculated? Can you go past it without causing damage? Sure you can. However, your heartburn level starts going up. And once you get down to, getting close to your ultimate, which is your ultimate critical or your ultimate pull strength, your heartburn levels should be right off the wall. So you don't need to stop immediately, but you do have to understand your materials and where you are in your design and then the strength of that material to be able to control your heartburn level and have a successful project. All right, with that, the reason I put in the geology section and the subsurface conditions is because that's what really controls your geometry of your drill. You can always design any sort of cantanoid geometry going down and back, put it wherever you want. However, if you don't put it in the right geology, it's not going to work, or it's going to cost you a lot more money. Well, you have a job that's going to cost you $7,500. Are you going to spend $10,000 to get geology? No, you're going to spend a lot less. So maybe you go look at locally available information. Call your local public works person. How you do the explorations to get that information, like I said, you can go to Public Works. You can look at local DPWs for what they have, or you can do test borings. All depends on your risk. As you find out that you have different types of problems, and one of the main ones is, am I drilling in rock or am I drilling in soil? Because that can have a multiplier of about 10 on your project cost. It costs you 10 times more to drill in bedrock than it would drill in soil. So that's an important question. You do want to get an answer to that. Lots of ways of doing it. And this is just, subsurface explorations. There's all sorts of techniques out there. Talk to your geotech engineer about how to properly, good enough, get the information you need. Next, please. Characterization. Once you have that in there, the next step is, say you have rock or soil, Now you want to know, do I have really hard soil? You know, characterize a little bit, give the driller a chance to figure out how fast can he penetrate this. So that's what all this is going to. Higher density soil takes longer to go through, going to cost you more. If you have a lot of water, maybe you have artesian water. If you have artesian water and you drill through it and intersect it, your whole hole can collapse, and it can cause all sorts of auxiliary problems like with people's wells. So look at all these types of risk that you want to characterize with your exploration and understanding what the data is telling you from your explorations. Things like cobbles and boulders, really bad idea. Not that it can't be done, but it's going to cost you money. Lab testing. There's a whole bunch of different lab tests that can be applied here. I'm not going to go through all of them. The reason for the assortment is there's different problems that can occur. Say you get a real sticky clay, you want to know about it so your contractor knows how to design the drill fluid so he can actually drill through it. Same thing on the unit weight. If he has drill fluid, it'll have an assortment of drill fluid weights. That'll give you an idea of how much ground strength you need to keep that fluid in the hole. So all these things, lab testing data gives you ways to analyze this using available like F1962, just one of the resources. I have a list at the end here, but use the lab to characterize things. Next, please. With that, put together a picture. Picture's worth 1,000 words. You can write this up in fancy geology language and be really precise and accurate, and find out that the driller has found a nice round file to place that in, and it's not doing anybody any good. Draw a picture, be clear, let the contractor know what he's getting into. It's a team effort. To be able to construct a hole requires a team effort. Your contractor and you as a designer and planner, you have more information than the contractor does with regard to what's in the ground. The contractor knows how to deal with it. Give them a chance to come up with a way to deal with it. Give them a picture. It works. Next, please. One of the risks are, there's a number of risks. If you hit different types of geology, you hit real hard geology and you don't notice it. That's the top picture on the left there. The curlicue rods, those are supposed to be straight drill rods. Actually, because they hit a boulder on the way across, they thought they were doing good. They kept on going and going, and by the golly, they never came out of the ground, walked to the alignment and found the drill rods up on top of the trees, all bent up like that. Well, helical buckling. Not a good idea. And it costs everybody a lot of money. Won't get into the story on that, but it can happen. Know what you're doing, know what the drill rods can handle. Other ones are like the bit balling up on the right there, etc. Other failures, but I'll move along here. Anyhow, once you have your risk, you need to evaluate, and this is where, again, your design comes in, evaluate things like, can you keep the drill fluid in the hole? In several common methods, Delft, the Queen's method, total stress method. It all is saying those little arrows pushing in on the hole are stronger than the little red arrows trying to push out on the hole. You can do that by design as a planning tool to help you select what depth to actually drill your hole in. That's where the importance and the difference between design and just drawing a line on a plan, saying, drill this line. This is the design method to come up with, where should I be drilling? Next, please. And it really does work. On the top middle there is a plot. I did that actually, that was down in Florida. You can see the prediction was lower than what we actually measured. The key thing is every time it went either sharply down or sharply up, or went off in Never Never Land there, like on the right-hand side, something was happening down the hole. I don't really look at magnitude, look at the changes, and that'll help you interpret what you've planned to see with what's really happening. The one down at the bottom just shows you the difference. Each of these techniques gives you different types of curves to work through as to whether you're going to keep the fluid in the hole or not. Know which one you're working with and understand the mechanics. Are you having a high factor of safety or a low factor of safety, so you don't wind up with that alfalfa field on the right filling up quickly with drill fluid that turned into a lake. Next, please. Anyhow, reference documents. There's a whole bunch of them out there. Most of these are freeware. Some of them cost a nominal amount. Every one of them has good information in it. Right down from MOP 108, which is a pretty detailed document, handles pretty much all types of pipe. Good practices, another very good document. 1962 is an abbreviated form that gives you mechanical equations and stuff, but in a little bit shorter format without the explanations that you get in the other manuals. PRCI is pretty much focused on steel pipe for directional drilling, and the PPI puts out an excellent handbook of PPI. Go to chapter 12, where there's several technical notes in there on small drills and large drills, and all the equations for using HDPE and how to select your pipe strength, your size of your HDPE pipe, your wall thickness. All that stuff is very heavily explained in that detailed handbook for you. It's a very good reference and it's free online. Next, please.
Awesome. Thank you. So before we leave HDD and go into slip lining, Brian, great job. We did get a question about directional drilling underneath the roadway and if there was any danger of affecting the stability of the road or causing sinkholes. So a lot of times transportation engineers, when we're trying to support flexible asphalt, they're very familiar with the stabilized subbase and everything that protects the flexible asphalt from damage. So they sometimes can't understand this concept itself, and I'm just posing the question to you to see whether or not it affects that road subbase as we look at it.
That's an excellent question. That's one of the reasons that HDD was disallowed for a number of years in several states. And Florida now has a guideline in there where you have to go a certain depth depending on your hole size underneath the roadway. Two things can occur. You can heave the road and create a large blister by losing your drill fluid by being too shallow, or you can erode a whole bunch of sand out from underneath it, creating a sinkhole. Note that the blister effect can happen almost immediately. However, the sinkhole settlement effect can happen weeks after you leave the site, and it can be a tremendous surprise to traffic, all of a sudden losing their front axle. So excellent question. It needs to be looked at very carefully and critically on any road crossing.
So interestingly, fellas, the HDD was invented by British Gas to save the streets of downtown London, and here we are, subtly modifying it and controlling it to make sure that we don't cause damage. But that is one of your primary responsibilities as the engineer on the job. Alan, I just want to mention here while we move into the next phase that we're at the end of 1 hour. We are planning an additional 13 minutes or so, and that we are starting to lose a couple people. We are encouraging you to stay till the end if you want to get your PDHs or your CEUs, but that we will be on up until 15 minutes after the hour, and we're running right on time. Great job, guys.
Awesome. Okay, so now we're going to talk about slip lining. Thank you so very much, Brian. We'll segue here, and I'll try to cover this as quickly as I possibly can for everyone. So slip lining here, we are taking advantage of the fact that we have an existing host pipe, and we're going to be able to pull a pipe in to that degraded pipe as we see it. So by using a plastic material, oftentimes we can get a much better friction factor in that new plastic material than what might otherwise have been in a corroded or older hose pipe for what we look at it. But we need to evaluate that integrity of that pipe to see whether or not this is a structural liner or semi-structural liner. We also wanted to validate the flow expectations for hydraulic analysis as we're looking through. We do have limited ability to pull through bends, so those would become an excavation point. Again, this is a trenchless technology, so it's not entirely void of trench, but we certainly minimize the amount of trenching that's required through that avenue as we go through it. So here you'll see some field-made pull heads to be able to distribute that force along this HDPE as we go through it. And again, this really highlights the robustness of HDPE as we're working with it in the field. So here we have a project as to which they've fashioned and fused on a pole head and took that over to be able to start to pull that into place itself. And then we see on the right here, they simply provided access to that pipe itself and then started to push that in. Richard, you want to come on and tell us, since you took this video, what we're looking at here?
Yeah, this was in beside the Miami airport. But this was a 60-inch, I believe a 60-inch steel line that was being rehabilitated. And they cambered that steel line first. And then the 54-inch, you can see the hole with the strap on it usually pulls that pipe in gradually as it went through. But the front end loader, which you can't see on the end of this particular pipe, which was I think 300-400 feet back, was literally pushing the pipe in. And I asked the head engineer there, I said, well, is that line clear? I said, because, you know, if you had any kind of disruption or unevenness in that steel pipe and it caught, that driver of that front end loader would have a little surprise. I think the opposite of a fly hitting the windshield, but the operator hitting the windshield. So there's a safety factor and a safety condition there, but they did push on. They eventually removed the strap because it just got in the way because it was wanted to get pushed in there. But that was probably a 2.5 minute 400-foot installation, a 54-inch in a very, very short time. But the host pipe was very smooth and very accepting for that to happen.
That's that pipe preparation that we're talking about. So then there's a difference between slip lining and then compressive fit slip lining. For compressive fit slip lining, you can only use high density polyethylene, and we're taking that OD of the HDPE, temporarily changing its shape to make it a smaller OD, pulling it through that existing pipeline, either through a die or a series of rollers or other things that make that activity go. And we are taking advantage of the material properties of high-density polyethylene to temporarily change its dimensions. Once we pull that line into place, then we will allow that pipe to relax, and it'll push up against the host pipes. So we certainly spend a lot of good time thinking about the preparation of that existing pipeline to make sure that there's no obstruction within that pipeline to be able to stop the compressive fit slip lining process as we go through. Again, any bends or anything within the system, we simply will not be able to pull through those, so they become now a point of excavation. Yes, Richard.
Yeah, so just a point, like, I mean, when you see a pipe get compressed like that, everybody asks, I've had several questions asked of me, well, does it affect the performance of the pipe? And the answer is no, because it's below the yield point, and that again references to the elastic modulus of the material. So there's no detrimental effects from pushing that pipe down to that smaller diameter and holding it under tension, because they are below the yield point in the graph. I think 9 to 10% in the yield point curve.
It's pretty cool, is what Richard is telling you. That's exactly what it is. So those final connections then can be robust, as we've shown before. All of the butt fusion equipment is designed to be removed from the chassis to be able to be lowered into that excavation to butt fusing in the hole in that manner. So pretty cool stuff. We'll talk a little bit about pipe bursting. Big distinguishment between slip lining and pipe bursting is now slip lining is often used for a pipe that we cannot burst. That you're simply going to pull that liner in. In pipe bursting, we're fracturing that existing pipe and pushing it into the 2 to 4 inches of soil that surround that replacement pipe as we go through. Both are very well proven technologies, commonly used all the time. A big difference between pneumatic pipe bursting and static pipe bursting is pneumatic can only use high-density polyethylene, and static pipe bursting can use other pipe material types for that production pipe. So we're simply using a constant tension winch to be able to pull that expander head to be in line with the existing pipe, and then a air compressor is on top to be able to provide compressed air to operate that expander head in a pneumatic scenario, as we're seeing here. These are some simple expander heads that we simply affix right onto the edge of the HDPE, and you pull that sucker along with it, then that area becomes sacrificial later. So you just cut that off and don't use it as your final production pipe. What you're seeing on the right then becomes a pilot, which helps us stay aligned with the invert of a gravity sewer pipe or a larger pipe as we come through. Here's a video for you. Pete's taken on a project in Napa where we're bursting asbestos cement pipe, and you're seeing that winch that's associated here. By the time that we get to the end of this pipe run, we don't have enough confining pressure on that pipe to be able to burst it through, so it daylights, and all of those pipe fragments stay in the soil surrounding that replacement pipe, as we're seeing here. Static pipe bursting does the same thing. It just provides the force in different mechanisms. We have a bursting machine in an excavation that provides that burst force, and it's driven by a hydraulic power pack on top. Here's some examples itself of using static pipe bursting for potable water. In potable water applications, we can seal that entire line in advance and then have it be disinfected. And that way static doesn't traipse anything within the interior of that pipe in that manner. Existing pipes that can be burst are shown here. What we're looking for is that complicated pipe matrix of a pre-stressed concrete cylinder pipe or something else of that nature that won't let us burst. So here you're seeing existing asbestos cement pipe being burst, and that fragment stays within the 2 to 3 inches of soil surrounding that replacement pipe. And then here you're seeing cast iron pipe that's being burst as well. So we've had questions over the years to see whether or not this pipe fragment scars or damages the high density polyethylene, and it does not. The technology is borrowed from British Gas. Had a sacrificial 3-meter section pulled in advance on every bit of it and studied that. And yes, Peter, we've got a few
Yeah,
minutes
those are
here.
great videos. Thanks for sharing. I just want to correct the record. I stated that HDD was invented by British Gas, and that was pipe bursting, Alan, not HDD. Martin Charrington is the icon of HDD. Thank you, Brian, for correcting me. I just wanted to clear the record. Alan, take it back.
Perfect. Thank you, Pete. I always like it when you get to point out where you're wrong, Pete, so that way I don't have to. So love that. So here's some examples of pipes that cannot be burst, and you can imagine why. So here's a simple classification chart that the IPBA has put forth, and we get into that size on size. It's just a class A type. When we get into developmental, that's going to be triple, quadruple upsize. So this is much bigger pipe as we're going through, much longer lengths, and then also bursting something like ductile iron pipe or something else of that nature. We originally want the best compacted backfill as we're pipe bursting through that, and that simply would stay on top as that expander head comes through the soil as we look through. Now, Brian had mentioned about the safe allowable pull stress, and the HDPE industry itself has significant resources available to you. This is just simple translated graphic from the published safe pull strengths that are found in PPI handbooks and other things that are available. Here we're simply looking at how we're fixing that pipe in the field. We are simply taking dry oilless chainsaws to it to work with it and cut it. In the middle section here, we found a gouge at 3 a.m. in this superintendent chin. He's just cut it out and fusing it right back up. Richard, you got something else to say?
Yeah, I'm sorry. I deleted a question because I was going to answer it online, but someone was asking about sewer lines and multiple connections when you're bursting. Yes, the answer is yes, you can burst them, and you just have to dig a pilot hole where those connections are for each one of those connections. Sorry about that because I lost the question. Thank you.
No problem, Richard. So here's some examples of pipe scraping that is okay. That's not within the 10% allowable gouge area. And then here's an example of something that's not okay. And this particular swivel did fail itself. So there's a big difference between gouges of what we would see that are acceptable and what we see that are not. So all pipe bursting projects, of course, do have the capability to have an unplanned pit, in which case each superintendent on site is prepared to be able to dig that unplanned pit to remove obstructions or anything else that we find, such as this boulder that you're staring at. So come on, everybody, for another 30 seconds here as we say our goodbyes. So it is that 75-minute time of the hour, and we made it right to the end as well. Here's contact information. The procedure for CEUs and PDHs are to answer question number 4 of the survey at the very close of this. And with that, Pete, do you have anything else to say, Nat?
No, I just want to say thank you to the hundreds of people that have stayed on and participated in this. I want to congratulate you, Alan, for a great deck. And Brian Dorward, I mean, really fantastic listening to you. And also, as we say, Alan, we offer these webinars, kind of think of them as your office hours. We entertain questions on any topic related to HDPE pipe. So Corin Main, Steve Breedemeyer, Rusty Reeves, great job. Thank you so much. Alan Ambler, Richard Klossa, Dusty Langston, and of course, Brian Dorward, our resident expert on anything underground. We'll see you next month, next week at the Alliance's webpage if you want to learn about cold weather fusion operations. So with that, I'll say thank you to everyone and bye for now.
Thanks, everybody. Appreciate it.